Okay? So when you draw that second velocity vector, only one of two things could happen. What are the only two options that could happen? Yeah, it either gets bigger because it's going faster, or it gets smaller because it's slowing down. So on number 15, what are you doing? Slowing down. So you just draw V2 like that. Okay, that's it. Now, because you're slowing down, which direction do your acceleration vectors point? Same direction? Opposite. Opposite direction. Okay? That's all you have to have. That's it. Do not make it complicated. Just V1, V2, you have negative acceleration. If it was speeding up, you draw V2 bigger, and then you point your acceleration in the same direction. That's it. Okay? That's it. The only thing you can do. So on number 15, what are you missing as a variable in number 15? Time. Which leads you to that equation. So I'm going to show you two ways you can figure this out. First thing you want to figure out is the acceleration. So if you solve this for acceleration, you get v squared minus v naught squared over 2x equals a. So that acceleration on number 15 should be around -5. Okay? So your acceleration should be around -5 on number 15. Now, the next thing it wants to do is figuring out how far it's going to go. Now, logically, you can make the assumption and you go, well, if I'm going 20 kilometers per hour and I stop in 3 meters, if I double my velocity and go twice as fast at 40, maybe I should take 6 meters to stop. Okay? That would be a reasonable assumption, right? But that's assuming that there's a direct linear relationship between velocity and stopping distance. But as soon as you see this v squared, can't happen. Okay? You cannot have a linear relationship as soon as you see that you have something squared. So there's two ways you can figure out the stopping distance on number 15. One is just smash mouth physics. You solve this equation back for x, and you go v squared minus v naught squared over 2a, and you plug in that acceleration, you plug in the 0, that new velocity of 11.1, and you find the distance, and it should be around 12 meters. Okay? That's the smash mouth physics approach. The more elegant approach is to realize, well, stopping distance is v squared minus v naught squared all over 2a. Well, if I keep the same acceleration, and this is why you look at this conceptually. Okay, well, if I double that initial velocity, that becomes v squared minus 2v naught squared all over 2a. Well, once I square 2v naught squared, it sounds weird, what do you get? 4v naught squared. So if this side of the equation goes up by a factor of 4 because you're doubling the velocity, what has to happen to your stopping distance? It has to go up by a factor of 4. So if your initial stopping distance was 3 meters, your new stopping distance is going to be 4 times greater than that, otherwise known as 12. Okay? So that's the other way. You really didn't have to do the calculation to find the new stopping distance. You go, okay, hey, it's squared. So 29 in the problems plays out the same way. And don't flip out and go, oh my God, it's just velocity v, and then we're going to double it to 2v. Okay? It's the exact same idea. You're doubling 2v and it's squared. What's going to happen to your stopping distance? It's going to go up by a factor of 4. Okay? So, there's that. Let's talk about question number 9 with the base of the softball player. So, here's second base. Boom, boom. Got the helmet on to be safe. Okay? And your initial velocity is 4 meters per second. Again, do not make this complicated when you draw the motion vectors. Are the velocity vectors getting bigger or smaller? So which direction does your acceleration vector point? Opposite direction. Okay? Do not make that difficult. Just draw v1, v2, put your velocity vector in the opposite direction. Now, your velocity time graph is going to look something like this. Here's 4 meters per second. There's a half a second. Right away, what do you know about the sign of your acceleration? Positive or negative? Negative. Negative is a negative sloping line. So there's a couple of ways that you can figure out that your acceleration has to be negative. One, your velocity time graph has a negative slope. That's option number 1. Option number 2, what's the sign of the velocity? Are you slowing down?
Yes.
Therefore, your acceleration has to be negative. So your acceleration should be between -5 and -10. Okay? That's what your acceleration should be. You're asked to draw a velocity time graph. You can just make a nicely drawn sketch off to the side. If you want to put it on a completely separate sheet of paper, you can. If you just want to draw it off to the side, that's cool too. But make sure you label everything that I want labeled on that graph. Okay? And again, view it through my eyes at 11 o'clock tonight when I'm grading your paper. Okay? Just keep that in mind. Now, let's talk about like how far did the runner slide? There's some different options that you could do. If it were me, I just go to the velocity time graph and I find the area underneath that graph. You know the initial velocity is 4. There's your height. The base is a half a second. Find the area. Okay? That's the easiest way to find the displacement. There are others. That's the easiest way. The other thing that you could do is you could do x equals 1/2 at squared plus v naught time. This is the most complicated way to do it. You know your accelerations, like let's say hypothetically -8. You know the time is 0.5 seconds. You know the initial velocity is 4. You can plug it into that. Mathematically, it's a lot of work, but you're going to get the same answer. This one is basically like a function equation. It gives you the function of position at different times, assuming you know the initial velocity and the acceleration. So if you've done function equations in math, this is a function equation that tells you position. Okay? That's all it is. Now, let's talk about E. You're trying to figure out the runner's velocity at 0.3 seconds. Clearly, what is your velocity at 0.3 seconds? What does it have to be greater than?
0.
0. But it has to be less than 4. Because you're at 0.3 seconds. If you're a math nerd, I'm giving you, you know the slope, I'm giving you an x value, I'm asking you to find the corresponding y value. Okay, so if you're a math nerd, that's how you can approach it. Would it be possible for your velocity at 0.3 seconds to have a negative value? What would that physically mean? You get a negative velocity at 0.3 seconds. What would that mean the runner is doing?
Going backwards.
Going backwards. So you're saying this person is going to slide into second base, at a half a second be at the base, but at 0.3 seconds she's going the opposite direction, but yet somehow at 0.5 seconds we end up at the base, which would be really, really weird. So obviously, this is just a slope-intercept form on part E. Just use V equals V naught plus AT. Your initial velocity is 4. You know your acceleration. You know your time. It's just plug it in. That's all you have to do.
For D, I got a negative number. Does that make sense?
For which one?
D.
Oh, no, you didn't. Oh, no, you didn't. You might have, but
Yeah, okay.
No,
That's
you
what I thought, but I was like, I don't know what I did wrong.
here, just find the area. Just treat it as a triangle.
Okay.
That's the easiest way to find that displacement. Without fail, that's the easiest way to do it. Okay. Your answer to number 11 should be around 11. Both of your answers to 12 and 13 should be around 30. That's an ish, but it should be around 30. On number 16, that acceleration on A should be around, this is just an absolute value, should be around 10. And the time would be a not so good GPA. Okay, not completely horrible, but could be better. On 17, that distance, excuse me, this is an ish, but it's around 60. And your answer to number 18 would make a really, 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 really bad GPA. 18.
It's wrong.
Okay. On the problems out of the book, okay? So again, at the end of every chapter, you're gonna have a problem section and you're gonna have a question section, okay? And yes, I know some of the answers are in the back of the book. I picked out the book. I'm well aware. I love it when kids act like teachers don't know that the answer's in the book. I picked out the book. Okay? I know you did. On number 5, question number 5, you should have 2 lines on that graph. You should have them labeled which one is the faster one, which one is the slower one, and when they pass. Me and the other driver is not labeling them. I don't do me and the other driver, okay? So on number 5, question 5 out of the book, you label which one's the faster, which one's the slower, and when those cars are passing each other, okay? Literally label them. Now, let's talk about question number 12. Because 12 is an interesting idea. So on number 12, here's your graph. You got one line that goes like this, and then you got the other line that goes like this. Okay? This is the position time graph. Wyatt, which one of those graphs shows constant velocity? Wyatt. Yeah, straight sloping line, constant velocity. That should be old school by this point. What do you know about the curved line? Is it speeding up or slowing down? Speeding up. How do you know? Line's becoming steeper. So, if 2 objects have the same velocity, how is that going to show up with slope on a position time graph? What do you know about the 2 lines?
They'll be parallel.
They're going to be parallel, okay? They're going to be parallel. Now, B, this is where you would want to talk about like tangent lines because of the fact that it's a curved line. So, when you look at B, is there a point where you could draw a tangent line that would be parallel to A? Absolutely, okay? So you can come in here and go, okay, there. So at that instant in time, when that tangent line is parallel to A, that's when they have the same velocity. Okay? So keep that in mind. Your answer to problem 30 should be around 30. Okay? Anything else you want me to go over?
13.
Ava? Out of the book?
Yeah.
Okay. Is that the one with the curved diagram?
It's like the dots. It's like which dot and
Yeah.
dot. That one makes it. I'm just smiling.
There was so many. What's your, is it 2D or 4D?
Okay, so let's talk about question 13. So, your book defines anything going right and up as positive, anything going left and down as negative. Okay, that's just the system that they use. So on 12A, it says, when is it moving the fastest? So this is a position time graph. So if you want to find the fastest moving point, are you going to look for the steepest part of the graph or the most shallow part of the graph?
Steepest.
Steepest. So basically, you're going to look at the graph and go, okay, where does this graph have the steepest point?
D.
Could be D. What about B?
No.
Why not B?
Because it's 0 stop.
Yeah, because what do you know about the velocity of B?
0.
0. Now, an interesting question. Speaking of D, did the object change direction at D?
No.
Why not?
Change direction at B.
But why didn't it change direction at D?
It's just.
That just means it went through the origin.
What's the only thing it did?
Then pass through the origin,
When past the reference point, how do you know that the velocity did not change?
because it's still going down.
Yeah, it still has some positive or negative slope to it, right? So the only thing that happened is that you were going in this direction, you turned around, and then you went past the reference point, okay? D is not a direction change. All it says is that you're going past the reference point. How many times does this graph show a change in direction? Once. Where?
B.
Because that's when you have a tangent line with a slope of 0. You gotta do three things to change direction. What are those 3 things? Slow down, stop, speed back up. Is that what's happening as you approach B? Yeah, because the line's becoming more and more shallow, it reaches 0, then it becomes negative.
So is B also the slowing down?
Well, let's talk about slowing down, okay? So, if you look on, like for example, on, let's talk about 13C, where it says speeding up, okay? So if it's speeding up, what's happening to the slope of the line?
Steeper. It's getting steeper.
It's becoming steeper, right? So, when you look at that in terms of when is it getting steeper? Well, clearly it's getting steeper from B to C. It's also getting steeper from, but then once you get past D, what does it begin to do?
Slow down.
Then it begins to slow down because the graph is becoming more shallow. Okay? Does that help?
So if it's talking about the points, it would only be C and D?
But you can talk about regions as well. So, like on 13 where it talks about speeding up, you could mention, oh, that's between B and C and then C to D. So you can talk about a region in that time.
Oh, okay.
It doesn't have to be necessarily a defined point. It could be points in between those.
How would I put that?
You could just put like B to C,
Okay.
something like that.
So, as we're coming from the reference point, we're going to the right, and then every turn it goes sideways.
Anything else? Yes,
11B.
Yeah.
with the graph?
Yeah.
Okay. This is why I didn't have you do 11A. Write a realistic motion short story. I'd have to like be Mr. Fry. Okay. Okay. So you got at the beginning. So you're given a position time graph, and you have to draw a velocity time graph that matches it. True? So here's some velocity time graph. At the beginning, what's the velocity of the object based upon the position time graph?
0.
Shanahan holds up a big fat goose egg. Why? What's the slope of a position time graph give you?
0.
Velocity. What's the velocity? 0. Oh, okay. So in your velocity time graph, just draw a horizontal line at 0. Okay? You're just at rest. That isn't bad, it's just not moving, okay? Now, then the line comes down like this. Is the velocity positive or negative?
Negative.
Why? Negative slope. Is the slope constant?
Yes.
Because so therefore the velocity is
Constant.
constant at some negative value. So how are you going to show some constant negative velocity? Yeah, just draw something like this. Obviously it has to speed up to get to that point, okay? So basically you're at rest and then you have some negative velocity. And that's what's happening here. Now, then the line goes horizontal again. So what's it doing next?
Back to zero.
Yeah, then you're back to being at rest, okay? Then, what's it gonna do? So, when it slopes back up, constant velocity, positive or negative? Boom, something.
You explain that, so please.
Okay, that's all you have to
I
do.
feel like I spent like 20 minutes, I said. 20 minutes on that.
Sorry.
What else? Okay, anything else?
Is 29, the answer to 29 a good GPA or a bad GPA?
I think
Now,
I was on
when
that.
you hand this in, first off, what are you not gonna have on the side of the paper?
The fringes.
The fringes. If you do that, I will immediately be in a fit of rage. When you staple this, staple my paper on the front, make sure that when you staple them, that the papers are in sequence, okay? The first, when I open it up to page 1, guess what problem I want to see? Problem number 1. One class got so bad, they would just hand them in random order. I told them, I'm gonna start grading your paper with my answer key. I don't care what the first page is. I'm gonna assume that number 1 is what it should be, and if it's not, kiss your points goodbye. So, make sure that it is done neatly, stapled, and in sequence. So, get that handed in. Ava, can you stop that camera for a second?